system.
So the topic is actually to deal with what happens is when we have air and water in ammonia refrigeration plant. Normally, as a human being, we want air and water in our body. But it's not actually true when we are talking about ammonia as a refrigeration system. So we try to see what happens as if today our refrigeration system has an influx of air and water. Let me show you some basic information. This is the requirement of purity of ammonia in our for our ammonia refrigeration plant. This is given by Association of Ammonia Refrigeration. So what it says that you need 99.95 pure ammonia. Why we say the purity of ammonia is because ammonia has got a very high affinity with water, and if water and ammonia comes in contact, then ammonia water mixes and it becomes hydrous ammonia from anhydrous ammonia. Our this refrigeration chart which we use for all our references, Nikhil was also talking about suction pressure and discharge pressure and other things. This all chart is related to the pure ammonia. That is our 99.95% pure ammonia. So when we are talking about minus 40 degrees centigrade, we are talking about say minus 4 psi pressure at the suction. It means this has to be, but this is possible only if we have pure ammonia. If ammonia is not pure, then this table is not going to remain valid and our system is not going to work. So we will see in our upcoming slides what happens is, so these two things, which is water and another thing is the non-condensable gases like air, nitrogen and hydrocarbons, which gets mixed with ammonia, affects our overall refrigeration system. And as Nikhil was talking about energy efficiency and performance, definitely these two things affect the energy efficiency of the plant. See, what happens is here, if theoretically for 13.5 kg, ammonia temperature has to be 35 degrees centigrade. Whereas the same pressure, nitrogen would have to be cooled down to minus 164 degrees centigrade to condense. So if nitrogen is present in our current ammonia refrigeration chart, it is not going to give any refrigeration effect, it is going to remain in a gaseous form. Same is the case with air or other. Now, how do we identify that we have air or the non-condensable gases in our refrigeration plant? The simple thing is that the total pressure in your system is actually a combination of a refrigerant pressure and the non-condensable of the air pressure. So pressure is additive. So pressure of your refrigerant plus air will be a total additional pressure. So when you are having this actual pressure reading for pressure gauge reading, it will be combination of your air pressure and your ammonia pressure. So how can you check that? See, normally your compressor gas and air both are entering into condenser. The ammonia will become liquid and the air will remain as air only. So what we can do, we can measure the pressure of your receiver and temperature of liquid. Now if you measure the temperature of liquid and convert it into corresponding saturated pressure, if there is a pressure difference between the two, that is actual pressure and the liquid pressure of the saturated liquid, then that difference is our non-condensable or air pressure. You can do it at your plant very easily and you will find out how much air is there in your plant. So what happens is when this air is present, as I told you, air does not condense or does not evaporate into our refrigeration cycle operating span of say minus 50 to plus 40 degrees centigrade. So it remains there and just moves along with the gas. So it's like a passenger traveling in a train without ticket. So what air does, it increases our power demand because the compressor is required to compress this air and rotate along with the system, and then it occupies the spaces in your condenser evaporator, which makes refrigeration system efficiency or the effect of refrigeration less. It also overall, because of both the things, increase in the power and decrease in the refrigeration capacity, it also overall decreases system efficiency. Now as the pressure increases because of the air, as I said it is additive, the pressure increases, the discharge temperature increases, and it increases more wear and tear of your compressors, the belts, drivers. Yeah. Now it is audible?
Yeah.
So increase in pressure leads to the increased temperature, which shortens the life of the compressor valves and promotes the breakdown of compressor. Increase in condenser scaling because of the higher temperature, and then of course it increases the maintenance of condenser and reduces the life of condenser. It also deteriorates or affects the performance of condenser. The one more possibility, which is ammonia explosion due to high temperatures increase in the discharge line. Ammonia, as you all know, it's combination of nitrogen and hydrogen. So due to high temperature, it is possible that this ammonia can break into nitrogen and hydrogen. So that will make the two gases present, and it will lead into the increase in more discharge pressure, because these both gases are the non-condensable gases. In a typical plant, you can see that the air will accumulate on the outside of the tube or into the inside of the tube. If your refrigerant is inside, if your refrigerant is outside, your air will accumulate on this tube, or your air will accumulate on the inside of the tube. In a typical evaporative condenser, again air will accumulate on this side. So when air accumulates, air is a bad conductor of it, and when air accumulates in these places, naturally the heat transfer affects, and the effect in heat transfer leads to the lesser efficiency of condenser. Now air normally accumulates on the high pressure side, that is into the condenser and receiver. Just remember that maximum air exists in condenser and receiver. This is a typical chart that if you have a 0.5% air, you have at least 1 psi increase in the pressure, and that will lead to 0.8% of power. Whereas if you have a 4% air, it will increase 7 psi, and power will be around 6.5 psi. In next slides, we will see how the power actually costs us. So the question comes in, where do I get my air in the system? Because my refrigeration system is a closed loop system. And by evaporating the liquid in evaporator, the gas is sucked by compressor, put it into condenser, convert it into liquid and store it to receiver. This is a one closed loop system, and this possibility of having any air coming in should not be there. But still we get air. Now air may get when we get the new ammonia. Ammonia cylinders may contain nitrogen or hydrogen and air itself. Because in India, when we are buying ammonia refrigerant, our suppliers do not provide us purity certificates. So there is no certification available what kind of ammonia we are buying. So these cylinders definitely contains air and water. Remember, when you charge ammonia from the system, you always have this air also going into the system. And particularly when you want to drain your all ammonia from the cylinder, how many of you try to kick the cylinder vertically upside down? When you kick your cylinder vertically upside down, the water inside the cylinder also goes into your plant. All cylinders have water. And when you tilt that cylinder, your water also goes into the system, air also goes. Then this is the year one normally source of getting air or non-condensable gases in plant. Then when plant is being installed, commissioned, we do the nitrogen testing, or many contractors do only the air testing. They just run the compressor and increase the charge the air into the system. So if that air is not properly removed, correctly removed, then it will remain into the system. Next part is that when you are doing the maintenance part, you are opening the compressor, charging the oil, charging ammonia. That time also it is possible that air will enter into the system. So these are various ways, one by which the air will enter. Another thing that we are from the freezing industry mostly. When our plants are operating below minus 33 degrees centigrade, it means we are operating in vacuum. So in vacuum conditions, when there is any leakage in the gland of a wall or any joint, then ammonia will not come out. It will be, air will go in. And when, because it is vacuum inside and outside pressure is higher, so outside air will go in. And this air will keep on going if there is a small leakage in the gland of the walls. And then when, as I told you, air starts increasing into our plant, our temperature increases, discharge pressure increases. So this also affects the oil in the system. And if this oil, which we are using synthetic or the mineral oils, they are again mostly made from the hydrocarbons. If this hydrocarbon breaks down, those hydrocarbons also become part of our non-condensable gases or air. And they also increase further our temperature and pressure of the condenser or discharge of the compressor. So what we can do is we have to remove this air continuously. The removing of air is what is called as the purging. Purging means we have to take the air out. Now normal two practices are there. One is the manual purging and another is the automatic purging. So we will see how the manual purging is done, how the automatic purging is done, and what are the advantages of automatic purging over manual purging. Manual purging, as we know, it is done manually. We have to go to the top of the condenser or a receiver, connect those hose pipes to, from there connect valves for outlet connections to hose pipes, connect it to the water bucket and drain it very slowly. So that there needs manpower. You need to shut down the plant, and it also affects the safety of human being is required. And of course, if there is air is not removed daily or regularly, it will be accumulating for certain time, and definitely so during the time of the two purging cycles, air will remain in plant and it will affect the performance. Third is that for this you need skilled labor. You need to use PPE kits, and that's cost. That is the cost nowadays because manpower is not very easily available. So what are the disadvantages of automatic purging? A disadvantage of automatic purging, one is that we have to have initial capital cost is required of purger, and then there may be a maintenance of the solenoid valves or other controls used into the purger. But overall, we can say that automatic purging being done online saves a lot. This chart shows us how the manual purging is done. That initially there is no air, slowly air starts accumulating. So at one point we start the manual purging happens. So again we come to the no air condition. But till our next time comes for the purging, air is getting accumulated. So this area is actually our energy or efficiency of the plant. This not only will affect on the system COP as Nikhil was talking about, but it will also affect the overall maintenance of the plant, increase maintenance of compressors, spare parts consumption and condensers. Whereas the manual automatic purging should maintain this line constantly. So as I said, three types of purgings are there. One is direct purging or manual purging. Second one is automatic purging using external compressor and condensing unit. Third one is using refrigeration system from the system itself. What is actually, when we are talking about purging, it means separating air from the refrigeration plant. So where we can do it from receiver, just provide a valve, connect it and put it into the water container and open this valve slowly. Preferably we have to do this, we have to shut down the plant so that there is no ammonia gas coming out of it, and you must wear all the PPE kit and safety equipments. Whereas in this is a procedure given here. Use a PPE kit, have a wall pipe connected on top of condenser and receiver. Now remember, when we are doing manual purging, the purge wall is normally connected at the inlet of the condenser, because when we stop the plant, the air will accumulate on the top of the condenser and then we can remove it. If you try to open the purging valve in running condition, not air but all ammonia will come out. So you have to make sure that your condenser is stopped, sufficient time of water is being sprinkled on the condenser so that all the ammonia inside condenser is full, liquefied, and then you can remove the air. So this is a complete procedure given here, and this has to be very thoroughly followed by all the people involved. Otherwise it will affect the human being operating it. Leakage of ammonia is possible. So as I said, it requires a lot of time because you need to shut down the plant, run the condenser, and then remove the air. And it is also, there is no guarantee that it will remove air 100%. Possibility of ammonia leakage is also there, so which is very dangerous for the people. And recently we have seen a lot of accidents taking place, particularly in Andhra Pradesh, because of the ammonia leak. Not only in ammonia refrigeration plant, but also in other industry. But ammonia is getting blamed onto it. So these things needs to be very carefully done. So another option for this alternative is to go for an automatic purging system. In automatic purging system, there are two types of purgers are there. One is using external condensing unit using compressor, and then there is another evaporator where this system is using to cool the. What is being done here is that it is installed above the receiver or condenser, and the foul gas is taken from into the compressor. It is condensed, and if there is ammonia, it is pulled back to the system. And if it is not condensable, it is vented out. The advantage of this system is that being a separate refrigeration unit, it can run when your plant is also not working. So what are the disadvantage? Disadvantage is that you need to have a separate compressor, separate refrigerant gas, separate condenser. So here we need a totally separate refrigeration system, which affects the maintenance of the, which means we need to maintain separate parts, spare parts for this compressor. Extra power is required to run this compressor, and the design is such that it has to be installed above the condenser or above the receiver. So connecting it to multi-point condenser or receiver is very difficult. You have to have very big arrangement for it, and then of course because it requires compressor, it requires regular power. This is typical purger installed. You can see above receiver. This is this well point, and it needs separate power. So the second type of automatic purging is using refrigeration from refrigeration plant itself. In this plant system, we are taking small refrigerant input from our refrigeration plant, cooling the coil and putting that gas back into the system. So if we are having 500 kilowatt or 1000 kilowatt minus 40 system, only 2 kilowatts are required. 2 kilowatts from that are required for this purger. So this purger does not require extra power or extra compressor to run, and it runs as long as the plant is running. There is no need for installing it above condenser or above receiver. It can be installed anywhere in the plant room, next to receiver, next to condenser, wherever space is available. The disadvantage is that if your plant is totally stopped, then it will not remove the air. But normally if your plant is not running, you don't need to remove the air. We need to remove the air when our plant is running. This one here, it shows the complete purger installed in the plant, having multiple purge points, liquid feed and the liquid return line. Now to make a purger or automatic purger work successfully, what is the most important thing is the purge points, or the points from where I am taking my air or the foul gases to purger. So what air purger is normally doing, it is taking the foul gases inside. There is a cooling coil or there is a cooler available which cools down that foul gases. So if there is ammonia, ammonia will go down, ammonia become liquid, and if it is non-condensable or air, the air will remain in the vessel. Now there is electronic sensors are available which is sensing the difference between ammonia and air. If there is air is vented out, and if there is ammonia, it will be liquefied and it is put it back into the system. So most important thing is to take the purge points, or the finding out the points where I need to take my air out. So what are these purge points? This should be in such a way that where air is getting accumulated. Naturally, if you want to remove the air, the point has to be placed where air is getting accumulated. Now where my air will come? Air will come into the, when my gas is entering into condenser, as I told you, it will be with ammonia and air both. So both have the same velocity. But when I go to the end of the condenser, the velocity of ammonia gas will be zero because it will become liquid. And what will remain is only air. So I have to take that air out. Same is the case when I am talking about my receiver. When my liquid is entering into the receiver, possibility of flash gases or ammonia present is very near to that point is there. But if I take it further away from the liquid entry point, then my possibility of only air coming out is very high. Now one more question is that should I purge from the air from the condenser or receiver? I says you have a purging points connected to both the places because accumulating air in receiver or condenser is both possible. But theoretically what happens is air will remain in condenser when receiver liquid temperature is higher than the condenser. What it means that if receiver is hot and condenser is cool, air will remain in condenser. And if air will go to receiver when condenser liquid temperature is higher than the receiver. So if receiver is under shade or receiver inside the plant room and condenser is above on terrace, then maximum air will come to the receiver. But I will always recommend to have a purge points connected to both the systems. This is what I was telling. This is your actually a manual purging point. So never use this for automatic purging. Always have a purge point at the outlet of the condenser. You see this is the manual purging point, whereas this is your automatic purging point. In a receiver, when we have a liquid entering into the system, make sure that you are taking purge point totally away from the this flow to this liquid entry point. Now this vertical, earlier they were using vertical shell and tube condensers, but again if you are having a liquid entry here, should have a purge point at the top. These are some of the installations of a Phe condenser. You see here at the outlet, before the U-trap, this purge point is taken. Same is on the evaporative condenser, purge point is taken over here. Or an atmospheric condenser, the purge point is taken from the common header. Do not take purge point. This is like your another installation where is outlet, the purge points are taken. Do not use U-traps for this purge lens connections. This kind of U-trap will trap liquid here and ammonia will not go into the foul gas will not go to the purger. This is a typical drawing of how to connect a multi-point purger in your liquid overfeed system. And this one is for the gravity feed system. I think AR will be upgrading these presentations on AR website. So you will be able to download all these presentations maybe on by Monday. So some of the case studies shows here that earlier the discharge pressure was 16 kg and when purger was put it into the operation it come down to 12 kg. This is a case study of a ice cream plant. So if you see they saved around 8 lakh rupees in a year just because they have removed the air from the plant. Other savings just like increasing the cooling efficiency, less maintenance, better oil, longer oil life, less condenser maintenance are not considered into this. This is, you can say, in a freezing plant for a 500 kilowatt where you need a 281 kilowatt power. If your actual pressure is 15 kg, and then when you put instead of 13.7, you have a 15 kg pressure. Your energy saving would be around 19 or 20 kilowatts per hour. So in 6,000 hours operation, you are talking about saving of around 9 lakh rupees, just because you are removing the air. Or if you have a small and -10 evaporating plant, still you are talking about 6.5 lakh rupees saving in a year. And these savings are calculated on actual case study basis
I have the reference data available, and other benefits such as the wear and tear of compressor parts due to increasing the earlier temperatures or increasing the improving in the cooling efficiency, condensing descaling or less condenser maintenance are not added into this. If you add this to all, this figure will go up much higher. This is a little bit about air, and let's talk about water now. As I told you, water has got very high affinity with ammonia, and it is because of which ammonia is very easily soluble into the water. Now what happens here is that at 30 degrees centigrade, approximately 30% of ammonia can dissolve into water, or water can absorb 30% of ammonia. But when you are at minus 33 degrees centigrade, or that is our, then 100% water can absorb into ammonia. It means our ammonia can become 100% hydrous ammonia instead of anhydrous ammonia. If you remember at the beginning of the presentation, we have seen the slide of purity of ammonia, where we say that we need 99.95% pure ammonia. And now, if your water is there, then naturally the purity will not be there, and the pressure and temperature charts which we have shown will not be effective. What it means is this is the most important slide. Theoretically, if there is 0% ammonia, or my ammonia is 99.95% pure, at minus 0.3 kg per centimeter square, I should get minus 40 degrees centigrade. Now, if I have 10% of water in my ammonia, I will not get minus 40, but I will get only minus 38. What this means, or for 30% ammonia, I will get minus 32 degrees centigrade only. What it means that if I want to get minus 40 degrees centigrade with 10% of ammonia contamination, water contamination, I need to run my compressor at still lower temperature. It means instead of running at minus 0.3, I may be running at minus 0.1. Now, as Nikhil has told us about the energy efficiency and COP is directly linked to the suction pressure and the discharge pressure of the compressor. So if I am reducing my suction pressure, naturally my COP is going to suffer, my energy efficiency of compressor is going to suffer, and because now the compressor is doing more work done, it means that my overall refrigeration capacity of the plant is going to decrease. It means I will not get the same refrigeration effect or capacity from the plant at the rated conditions. Now, if my ammonia is 20%, I am talking about minus 36. So, to get minus 40, I may have to run plant at minus 0.5 or minus 0.6. So naturally, my overall efficiency is totally deteriorated, and I will not get the desired temperatures. Secondly, this water will make a lot of other things into our plant. We will just see what happens is when the water is there. Just try to see now from where the water comes. So the water can come from during installation and commissioning activities, or water can come into the normal running hours. So when a plant is being installed and commissioned on the site, many manufacturers do the hydro testing. We as a AR do not recommend hydro testing. We recommend that all the pressure equipment must be pressure tested using dry nitrogen. But unfortunately, the dry nitrogen needs some money, so many manufacturers prefer to use hydro testing. Now that hydro testing means they are charging the water into the vessels, and that water is not completely drained. So it is possible that water will remain into the pressure vessel itself. That's the one big way of getting water into the system. Another thing is that when your installation construction is going on, many times pipes, pressure vessels, equipments are lying on site. Their ends are not close connected, or pipes which have come with the plastic caps are removed. So the condensation in the night will get occurred into the pipes. This pipe will not be cleaned before installation by the installation contractors, and that condensation will remain in water form. Then many people, as I told you, they use air while doing the pressure testing. Now how they get the air? They simply run the compressor, keeping the suction valve open. It means they are taking the atmospheric air. Now the atmospheric air will also contain the water or moisture. Now that moisture will remain into the plant. And once that moisture is inside the air, even though you remove the air later on, that moisture will not go. It will remain into the plant itself. Because it is very difficult to dry the plant when you are charged into water into it. Third part was I am telling you, when you are buying ammonia, unfortunately we do not get purity certificates. Our vendors do not give, we do not insist for the purity certificate, and they do not issue us a purity certificate. So the ammonia may contain water itself. As I told you, when we keep the condenser, this ammonia cylinders 180 degrees, then if there is a water in the that cylinders, it will come into the plant. Now when the plant is commissioned and plant is running, there are other ways of getting water into it. One is that your heat exchangers, either condensers, evaporators, where those tubes or the plates are in contact with the water, there may be a leakage between it and the water will enter into it. And then when your plant is running, when you are charging oil or removing oil, then also possibility of water will get infiltrated along with the air. Secondly is that I was telling about getting air into the plant. When plant is running in vacuum, then certain moisture from the air also will get into it. Even though your purger will separate out the air, the water will remain in the system. And then this overall, what happens is because of this, the water will continue to remain in system. Let me tell you how the air purger actually gives us indication of getting water into system. Let's assume that our purger is removing 5 liters per minute from our plant. Our ambient condition is 35 degrees centigrade, and when we are in coastal area, the RH could be around 70-75%. It means it's a high humid area. Now whenever this 5 liters of air is entering into the system, for 75% RH, we will be getting 25 grams of water per liter of air. So when we are talking about for running for an 1 hour and air purger removing air for 1 hour, it means that we are also getting 7 grams of water per hour in our plant. So when air purger is continuously removing air, it means there is some way the air is continuously entering into our plant. It also indicates that water is getting into the plant. So if we are just having a 5 liter air being removed, we are talking about accumulating 45-50 liters of water in a year, which will not be removed. Now what happens is because of this water, as one is that main effect we have seen on the suction and the discharge, on the basically the compressor ammonia pressure temperature chart, which will affect our suction pressure. Now it will also affect the corrosion in the refrigeration plant. Because there is a water and air, the oxygen in air will help water to corrode. Our plants are made with steel, so corrosion will start inside. Then water will affect oil. Oil aging process will be much faster with addition of the water. Now when oil is mixed with water and ammonia, it will form a solid gum, and it will like a sticky things. It will get stuck into compressor or many other parts. And then this sludge will get accumulated in your filters, choke filters, compressors. So of course compressor wear and tear will increase, oil consumption level will go up, and overall maintenance service cost goes up. Now as there is a sludge formation in the pipelines on the walls, there will be more pressure drop into those areas because of their creating restrictions, and then your overall efficiency will affect. Pump performance will affect, and as I said, suction pressure, you need to operate at lower suction pressure, so it means you need more power. So overall efficiency will go down and increase the electrical energy cost. These are some of the photographs which I have collected from various sources. Like these photographs were shared by our Mr. Dhananjay, who is mainly expert into compressor servicing. If you see this mixing of water and sludge formation of oil has damaged those bearings of compressors, and the screw compressor internal parts are damaged. In a typical piston compressor, instead of oil having the oil level, you can see that this filled with water, and when we are removing the oil, it's all sludge and oil filters are chopped. Biggest effect will have on the bearing life of the compressors. Because of the water, the bearing life will keep on reducing, and your frequency of replacing bearings will be very high. So where water will accumulate in my plant? Like I said, air will accumulate on the high pressure side. Water will always accumulate on the low pressure side. Because it can be in low pressure receivers, it can be evaporators or surge drums, suction accumulators, and if you have two-stage system like Nikhil was talking about, high-stage booster system or compound compressor system, it will always accumulate on the low pressure side. The reason is that there is a vapor pressure difference between water and ammonia. Like for 2 degrees centigrade, ammonia pressure is around 3.6 kg, whereas the water pressure is 0.07 kg. So when the ammonia is evaporating at 3.6 kg, all the water will remain into the evaporator. So this chart shows us water pressure difference and ammonia difference at various temperatures. If you see, the temperature difference is so high that water will always remain accumulated into the evaporator side. It will not evaporate. So question comes in, can I find out or quantify the water in my refrigeration plant? The answer is yes, we can do that. We need certain precautions and equipment to quantify the water. So we need an ammonia evaporative test tube system, and then we need to use PPE kit, hand gloves, face shield, so that you will not get into trouble. What is system is that you connect this, like it says, locations are from the pump discharge line or the low pressure receiver from the drain of the walls in the evaporator side. This is a typical ammonia sampler system. You connect this wall, you can see, right, this wall to your low pressure side. You take a measured quantity of the sample for say 100 ml of ammonia, and then you close this wall. Then you let it ammonia evaporate from this tube. So whatever is remaining will be ammonia. This is a detailed procedure how what I have told you about how to take this. So if you see, this is the actual system connected from a pump header. It is connected over the was filled with ammonia, and then slowly ammonia evaporated, and you can see here around 6% of water being found out into the system. So this tells us that you have a 6 or 7% of water in the system. So it totally affects your, will understand how much it affects. So can I remove this water? How do I remove? Because what we talked about is ammonia and water are have affinity, means they mix together. So how do I remove that? So we have a device called ammonia dehydrator, ammonia removal system. What it does is that it takes the samples of ammonia from low pressure side, and then there is a provided with a external high temperature ammonia liquid. So this ammonia, like whatever the ammonia is accumulated into this vessel, it evaporates and goes back into the system. And what is remaining, it remains the water in at the bottom of these things. This is your typical installation drawing. From LP vessel, you are taking the samples of the ammonia for purification, and it is going back to the LP vessel. Whereas your high pressure line going from high pressure receiver to LP vessel or to intercooler is rotated through this vessel, which provides the heat source. So typically, this is a very simple installation, and it saves a lot of, and it can be removed online. how much power or how much wastage of water I can save. Typically for 300 kilowatt booster compressor that is on low side with minus 40 evaporating and minus 7 condensing, instead of operating minus 40, we are operating at minus 42. Then we are talking about saving of rupees 7,75,000 in a year when the power cost is around 8 rupees. If your power cost is more, naturally your saving will be more. And if you are having similar two-stage compound refrigeration system, then you will save around 4,80,000 rupees. I think this some calculation mistake is here. So it will be more than that because energy saving is 10 kilowatts. So what we talk about today is how we can save energy, can improve the performance, and what air and water does. So air increases the discharge pressure, increases the power consumption, overall reduces the refrigeration capacity, increases wear and tear of compressor, damages oil, and of course scaling on the condenser. So by removing air online, we can save a lot of money. Same thing is that water accumulates on the low pressure side, and when there is a water presence, the system efficiency goes down, suction pressure has to operate on lower, electrical cost of the compressor refrigeration capacity required is there. Lot of corrosion can happen. The oil will damage frequently, and it will damage other parts of the refrigerant system also. So it will of course increase the energy saving cost. So what I have here is just two small videos of how air purger and water is removed from the system. You can see here that the air is bubbling through this bubbler and is coming out of from this purger. And the second video is a very fresh video taken yesterday only, and you can see already one bucket of water oil has been removed, and then he's removing one more bucket of oil, and you see how much oil has been drained from the system. So this way you can remove air, water and oil from your refrigeration system and make your plant more efficient, and of course it will save you a lot on to your plant maintenance cost and increases the safety of the plant. So that's all from today. Thank you very much, sir.